Okay, so now we're going to start in part two of life out there. And what we've discussed so far is life and its characteristics on Earth. And basically, we are going to need to look for water. That's our primary search technique. Although we need to, let me tell you, that perhaps we should be looking for alcohol as well. So these are the planets and bodies out in the solar system that we know have liquid water as far as we can tell. Obviously the Earth, Mars at one time, and perhaps it has liquid water still in various specific conditions. But also we have the moons Europa and Enceladus, and then we have the moon Titan, which may be have a life forms based upon alcohol. Okay, so we'll talk about that in a moment. All right, so let's look at Mars. And I don't know about you, but this top right-hand corner of the photograph looks pretty obvious as far as, those are river or stream beds. And then on top of it all, the Opportunity rover found these rocks, and they were hematites. And the only way you can form those hematites is underwater. There is also other indications of liquid water, and that's basically in the polar regions. They could be underneath the carbon dioxide ice, glaciers or whatever you want, ice caps, both in the north and the south, but underneath them could be water. Remember, if I get water on the surface, then it's going to immediately sublimate, turn into a gas, and then escape. But we did land the Phoenix spacecraft in the North Pole, and we did find water. Now, there's also other indications of water on the planet where we notice in particular regions a new gully forming after a spacecraft has gone by and taken, pictures. An orbiter has taken pictures and then come back a time later and a new gully is formed. So the thinking is that, there was some water that was spritzing out and then, immediately vaporized, but was there long enough to create a gully. So those types of things possibly exist. And, there could be, besides that, it could be like the tundra up in the north here, where it could just be underground and thereby protected. Europa is another example of perhaps a situation with water on the moon. On the surface, it's basically covered in a sheet of ice. But if you look carefully at these sheets of ice, you see characteristics that look almost exactly like fault systems here on the Earth. Notice here, this one, we have some of them that are shifted relative to each other. And that is indicative of, plate tectonics, if you will. Here's an example right here where, it goes here and it looks like it's gotten shifted a bit, sort of like what has happened on the San Andreas Fault and the Garlock Fault here. So the idea is that we have this surface, which is ice, and then underneath it we have a liquid ocean. And remember, there's heating of Europa caused by its orbit around Jupiter and its interaction with Io and, I believe, Ganymede. Okay, remember that they are operating in a 1, 2, 4 orbital period resonance. So Europa is getting squished and elongated, squished and stretched, and that's causing this liquid water to form, some heating going on, liquid water to form, and then the outside surface is frozen. Enceladus is another example. It's instead around the planet Saturn, and we also see that it's covered in ice. It has the most reflectivity of any object in the solar system, and we believe this is what is causing Saturn's rings to be white and so bright. because we have geysers coming through the surface. And so if we have geysers, then we must have liquid water. And I believe also the Cassini spacecraft has gone through these clouds and has determined that there are carbonic molecules in these clouds as well. So chemistry, maybe? Our last one is Titan. And recall I was talking about alcohol on this. Instead of looking for water, we should be looking for alcohol. And the reasoning is this. There's basically a lack of hydrogen and acetylene on here. And one of the thoughts is that we have organisms that are creating methane out of hydrogen and acetylene, and they are producing, and that's instead of utilizing oxygen and glucose to create CO2. Don't let it be said that humans are not don't come up with some interesting ideas. A lot of this is still in the formative stages, but this is how you come up with ideas for sending spacecraft out and what kind of instruments to put on them. So this is something that, these two, or actually these three moons are ones that are going to be looked at in the not too distant future. And as you know, we're constantly looking at Mars to see what's going on with it. Okay, so what about all those exoplanets out there? So, this is an orrery of all the exoplanets that were available for a while. And let's see, at some point in time, this thing goes for about a minute. And there are roughly somewhere around of the order of 3,000 or 4,000 planets that have been observed out there. The planets going around other stars. And I just wanted to show you this. And we do have some understanding about the temperature of the planet. We do have an understanding about the star that it's going around. Things like that. So we do have some information about what's going on there. So the next step is to see if there's life out there, and as we've indicated, we are after certain, things. We want to find the water. Okay, so let me remind you about this, that when we're looking for exoplanets, one of the techniques is to look for transits, and the Kepler spacecraft was really, really good at that. And so the idea is this, is when a planet goes in front of the star, then the amount of light that is observed is at a maximum, right? Because the planet is not in front of the star is not being occulted at all, and you're seeing the whole disk. Now, when the planet gets in front of the star, then the star's illumination is going to decrease. And it will stay decreased for a while until the planet moves off. Well, another way to turn that on its head is let's take a continuous spectrum of what's going on. And when we're looking at the star by itself, we're going to only get the elements from that spectrum of the star. But then if we have the planet in front of it, then we're going to also see a decrease in the amount of illumination. But during these regions, if the planet has got an atmosphere, then that atmosphere is going to get irradiated, it's going to get energized, and those elements in that atmosphere that will then relax and emit light of their own. And so during this period of time, where the planet is in front of the star and the atmosphere is energized, if we take the spectrum there, we're going to get planetary and stellar elements observed. So naturally, all you got to do is subtract this spectrum from this one, and pop, there we get the planetary atmospheric elements. And then what we want to do is find out if there are any biomarkers out there for us. Now, what are some characteristics of life that we see in our planet? Basically, these are ones that I can come up with. Molecular oxygen. On Earth, that was a byproduct. It turns out that you and I utilize oxygen to convert glucose into carbon dioxide and structural components, but plants utilize carbon dioxide and create oxygen from it. Oxygen is a byproduct. And then if you have an interaction with that molecular oxygen and the star, you create ozone. And we got a nice big hole here for ozone. If we've got water, as we keep on telling ourselves, water seems to be a requirement. It's the universal solvent. So if we got water out here, then we've got perhaps life. And then if we got CO2, okay, well, CO2 is needed by plants. And then on top of everything else, methane is our primordial gas, atmospheric gas, but methane and oxygen don't like to live together. And then we have this thing called the red edge of chlorophyll. Oh, chlorophyll, you know what that guy does. So in more detail, molecular oxygen, plants create it, and we get CO2 and water, and it's very obvious. This is a byproduct of O2, so you got to have life in order to create it. And then, carbon dioxide, obvious, water vapor, obvious. Now, the methane isn't so obvious, but if you have oxygen in the atmosphere, methane can't be there because it would burn off. In order to have methane in the atmosphere, you have to be constantly creating it. You and I create some, but basically we're going to pin this problem on sheep and cows, okay, and pigs and, those sorts of things. And so those two are really, methane with oxygen, that's like, obvious. And then we have this sudden increase in, the red edge of chlorophyll. So pretty amazing stuff. Now, is there evidence for this? Not much yet. I have some websites here that I intend to look at a little bit more carefully. But Sarah Steiger from MIT has done some research on this. I am not expert enough to know if it's dead nuts on, if you will. And then Michael Richman has a class on exoplanets at RIT, and so there is a section there on atmospheres there. And then if you look at ESA and NASA websites for the spacecraft that are coming up, they'll talk to you about the premise, the theory behind looking for these atmospheres. But I'm still not sure if we really have good evidence of this. Okay, so that's to come up next. Not my next charts, but it's something to look out for in the science. Okay, so we have some ways of figuring out if there's life out there, at least as far as we should be looking for, and it isn't too clear yet if we found it yet. But perhaps we ought to jumpstart this whole criteria and see, why not we start talking to these guys or, listening for them if they're out there. And so one of the first questions we would want to ask is how many should we expect? And that comes out of this thing called the Drake equation. And the Drake equation is a specific a specific example of what's called a Fermi problem. And a Fermi problem is one that I would have my students take a look at, which is this type of problem. And the basic idea is this: in order to characterize something that we don't know, we break the problem up into pieces. And if you look up on YouTube or Lawrence Krauss in The Secret Life of Physicists, he does a couple of Fermi problems. And then, for example, one, how many piano tuners there are in London, how many atoms of oxygen are you breathing that Caesar breathed his last, et tu Brute. So, we start off with some basic ideas, and then from that we can determine the answer. So here is an example for you to work on. I have my students work on this one, and that is how many grains of sand are there on the Earth's beaches? Now, this, when people first look at this, especially in my classroom, it's like they have no clue. They just don't know where to start. But the starting is if you take a step back and you think about the problem and think about what you know and how you generally solve problems, then this problem becomes very easy. Okay, so what is the question asking you? How many grains of sand are there on the world's beaches? So we need to define what is the question. What is a grain of sand? What are the world's beaches? Okay, well, let's start off when, it's asking for the number of grains, so it has to be something I have to look at a sand and compare that to a beach. Okay, I know that sand grains are on beaches, right? And and I am immediately drawn to size. A grain of sand is a certain size, and a beach is a certain size. Now, I have been to beaches, quite a few, and I'm certain that you have been to quite a few beaches. And the more beaches you go to, the better idea you have to characterize what is a characteristic beach. And when you characterize the beach, you're characterizing its size. What is size? Well, size is the length, the breadth, and the height. So length times width times height. Okay? Well, for a grain of sand, I can imagine a grain of sand on my hand and how big it is. And then if I go to the beach, I can characterize its length, its width, its height. But its length represents kind of a problem because one beach goes into another, goes into another. So isn't there a way of characterizing the world's beaches by just saying, okay, it's the region in between the sand, between the water and the land. So it's the length of the coastline. Okay, so the length of the coastline represents the length of all the world's beaches, and now I need to come up with just an average depth of a beach and an average width. Now, from there, I'm not so sure I could figure out exactly what is the depth of the beach, but I could say maybe it's, 5 to 10 meters. Okay? And then I can characterize the width of the beach because I've been to a bunch of beaches and some of them are very narrow and some of them are very big. So let me just take the average. And the average is, say, maybe it's a football field, so 100 meters. Okay? And if I keep it like this, then it becomes pretty simple. I've got the length is the length of the coastline. Okay, and if I take a look at a globe, I can characterize the length of the world's beaches by the length of the coastline, and I can compare that to the radius of the Earth by using a globe. So now I have length times width times height, and now I compare that to the size of a grain of sand. Dividing one by the other gives me the number of grains. So the same thing was done in regards to trying to figure out how many civilizations are out there that I can talk to. And it basically breaks up the problem into various pieces of that which I want to figure out. So the number of communicating advanced civilizations in the galaxy is what I'm after. And what is necessary? Well, what is necessary is I need to have a civilization. In order to create a civilization, I need to have intelligence. In order to create intelligence, I need to be alive. In order to be alive, I think I need to be on a planet or something that looks like Earth. And then if it's a planet like Earth, then I need to have a planet. And in order to have a planet, I need to have some energy on it, so I need to be on a star. I need to have it going around a star. And so part of the civilization is I need some amount of time to talk to the civilization. So the lifetime of the civilization seems to be a necessary part of this parameter. And so I need to also figure out how many stars I have at any particular moment. And that's sort of the going rate. How many am I creating at any particular time? And all of these numbers sort of cancel out, right? This is a rate, so that's the number of stars per year, if you will, and this is also in years, how the lifetime of the civilization. So if I multiply all these guys together, then that comes up with the number of guys I can talk to out there. And now we can just basically argue about what are the reasonable numbers to put in here. So, what are some reasonable numbers? Well, it seems as though we have pretty good, this chart I put together about 5 or 6 years ago, and these numbers change. But at that time, we were thinking that at least for a galaxy like our own, we're creating about 10 stars a year. Maybe it's less. I think we're finding that there are planets going around every single star. Every single one of them that we look at, it's got planets. We do have a problem that we have all these hot Jupiters, but maybe we got a handle on that. And then we need to figure out, okay, the number of Earths we got going around that solar system, or basically what are the objects that can support life. And so we've got 4 candidates, maybe 5 candidates around our own solar system. So if we're comparing this to how many planets we've got, then it would be, we only have 1 planet. That's Earth, right? But we also got Mars, which was a possibility at one point. We also got Enceladus. We also got Europa. And we also got Titan. So maybe this number, 1/10, is kind of on the small side. What is the probability of creating life? Well, it took only 1 billion years here. And, there is evidence from that meteorite and some meteorites from Mars to indicate that there are perhaps bacteria on those things. So maybe life is just, standard process. Intelligence? Well, we actually have quite a few different species on this planet that are intelligent. Not including us and our great apes, but think about cetaceans, and then you've got organized societies like ants and bees. So maybe intelligence is, is pretty prevalent there too. Now this one, if you create intelligent life, then to create a civilization, this is getting kind of iffy. Because what we mean by civilization is something that creates radio telescopes, because that's what we're going to be utilizing to communicate with. And then the lifetime is also a questionable amount of, it can vary. I mean, we've almost destroyed ourselves a few times. But then again, you can take that on either end. One is that we're going to kill ourselves, and the other one is, well, see, we've missed out a few times already, so maybe we'll last. And so you can come up with some very large numbers. But even with the number of civilizations being 1 million, consider this, that the galaxy, and this was done for the galaxy's got 100 billion stars in it. So if I have 1 million of these things, then I could also say, well, on average, each civilization has got, 100,000 stars to call its own? And so that would mean that my nearest neighbor, if there are 1 million civilizations out there, my nearest neighbor is 50,000 stars away from me. Just in round numbers, right? And if I do what comes naturally, I would say, okay, each star is roughly the same distance away as from here to the nearest one, which is about a parsec, so 3 light years. So if I'm 50,000 stars in size for my civilization, that means my that I've got, I probably don't have those numbers right, but, at some point I'll fix them. But basically, you see, I'm getting into really large numbers for distances. And so it doesn't seem quite possible for me to go out there and visit. On the other hand, I could also have a very small number. So that could mean that I'm really here, that we're really here by ourselves, and we better take care of our planet. All right. In the next section, we'll talk more about looking for extraterrestrial life, and basically, should we go out and look for them? Either listening or talking, or going there. And then that will be the end of this section. Okay, thank you very much.